Okay, let's discuss two different graphs pertaining to limits, and in one case, a point of discontinuity, in another case, a function that does not have any discontinuities anywhere. It's continuous everywhere. So in this case, function g, let's look at the discontinuity position at 0. So the first thing we want to answer is, what happens to the function as x approaches 0 from the left? Now we're using limits terminology here, so we've got the limit of g of x as x approaches 0 from the left. So what is y doing? What is the output doing just to the left of 0? So we're to the left of 0 on the graph, and we're approaching 0 from the left. Well, the function is behaving like 1. Now we can see on the graph that there's an open circle at 0, 1. However, the limit again is a descriptor. It does not care about exactly at that position, but just a little bit to the left. Okay, well, what about as x approaches 0 from the right? So as x approaches 0 from the right, we're over here. Now, as we approach 0 from the right, the function is going downward forever without bound, and it's behaving like negative infinity. And we use negative infinity here to tell the description of what is happening to the function to the right of 0. Now, the next question says, what about x approaching 0? There is no plus, there is no minus sign here. Well, that means that we're talking about the double side limit at 0. We've got a one side limit, a left side limit that equals 1. That was this part. We've got a right side limit at 0 that equals negative infinity. Okay, to explain our behavior here. That tells us that our double side limit does not exist. We'll use DNE as an abbreviation for does not exist. Now, the reason that this limit does not exist is that we have a left side limit of 1, which does not equal the right side limit at negative infinity. And again, that's what's happening to the right of 0. It is going downwards to negative infinity. Okay, what about the function at 0? Now, the function at 0 is defined. It has a point right here of 0, negative 2. So the function is defined at 0 to be negative 2. The output is negative 2 when the input is 0. And again, we've got right side limit is negative infinity, left side limit is 1. Double side limit does not exist. The function at 0 is negative 2. So all of the four parts here are different. Now, the last two parts we want to talk about are the end behavior to g of x. So what happens as x approaches negative infinity? What does the output look like way to the left on this graph? Now, we can see that we've got a linear piece to the left of 0, and in this case, that linear piece is going upwards forever, okay, which tells us that it is divergent, and it's going to go to positive infinity here. Okay, and again, we're using it as a descriptor to talk about the behavior, and in this case, end behavior to the left. Lastly, for this problem, we've got what happens to g of x as x approaches positive infinity this way. We've got end behavior way to the right. Now, this is going to positive infinity as well. This function diverges in both end behavior directions, to the left and to the right, and both divergence are increasing without bound, going to positive infinity. Okay, the last graph here that I want to look at is a graph that is continuous everywhere. It looks like a cubic graph that has been translated. It's got a spot at 4, 1, and the position 4 for x is what we're going to discuss. We've got left side limit behavior at 4. X approaches 4 from the left of the function. We've got right side behavior at 4 of the function. Double side behavior for the limit at 4 of the function. and then the function at 4. Now, because this function is continuous everywhere, all 4 of these parts are the same number, and they are 1. 1, 1, 1, 1. We've got the left side limit is 1. We've got the right side limit is 1. We've got the double side limit is 1. And we've got the function at 4 is also 1. Now what that tells us is that this function is continuous at 4. And as I've already discussed, this function is continuous everywhere. And again, it falls under a branch of functions that are called polynomials. And polynomials are continuous everywhere. So for every real number value of a polynomial, we have the left side limit, right side limit, double side limit, and the function will all give the same value at a real number value for any polynomial function. All right, what about the end behavior of this continuous function? Well, as x approaches negative infinity, we can see it is going rather steeply down, but without any other descriptor there or an asymptote to show that we are bounded in some direction, we know that this graph is going to continue, and we are going to say that it is going to go to negative infinity as a descriptor here, the end behavior to the left. Now the end behavior to the right, similarly, we're going upward, we're increasing without bounds, so we're going to say that this end behavior is positive infinity. So we've got one graph that is continuous everywhere, left side limit, right side limit, double side limit, function are all the same. Answered end behavior for this function. Previous one, we had a lot going on at the value where x equals 0. We had something different. We had a left side limit that's a real number, right side limit that's not, double side limit that does not exist, and a function defined elsewhere at that value, in this case x equals 0.